Thank you, and welcome to our third MIDRC seminar presentation. This one is given by Dr. Berkman, who is a senior biomedical research scientist with the Office of Science and Engineering Laboratories at the FDA. He holds a PhD in electrical engineering and computer science from the University of Michigan, Ann Arbor. Before joining FDA, he was an associate professor with the Department of Radiology at the University of Michigan. At the Division of Imaging, Diagnostic, and Software Reliability at the FDA, he performs research related to the evaluation of medical imaging and computer-assisted diagnosis devices, including devices that incorporate machine learning and artificial intelligence. He has authored over 130 peer-reviewed journal publications, is a fellow of SPIE and a fellow of AMBI. Among other awards, he received the FDA Federal Engineer of the Year Award in 2013 and the FDA Excellence in Analytical Science Award in 2021. His interests include machine learning, computer-aided diagnosis, image perception, clinical study design, and performance assessment methodologies. So we are looking greatly forward to his presentation today on task-specific performance evaluation metrics for machine learning algorithms employing MIDRC data. Welcome, Berkman.
Thank you very much, Maria, for that very nice introduction. I hope you can all hear me and see my screen.
Yes, we can.
Wonderful, wonderful. Thank you very much. So again, my name is Berkman, and I'm with the Division of Imaging, Diagnostics, and Software Reliability at the Office of Science and Engineering Labs, Center for Device and Radiological Health, U.S. Food and Drug Administration. And today I'll talk about task-specific performance evaluation metrics for machine learning algorithms employing MIDRC data. Here is my disclaimer as an FDA employee. I'll give you a few seconds to read it. Okay. Here's an outline of my presentation. First, I'll talk a little bit about the motivation for the work we're doing at Technology Development Project 3C in MIDRC. Then I'll describe our current work where we're designing a decision tree for task-based evaluation metrics. I'll talk about the methods we're using to design the decision tree, and I'll give you a demo through an example task. I will summarize at the end. We all know that not all metrics are appropriate to evaluate performance for a given task. A well-known example is overall accuracy in a classification task, where the overall accuracy is defined as the number of correctly classified cases or the total number of cases. This is not a good metric by itself when a classification task involves a situation in which the prevalence of a particular class overwhelms the others. And we know that this situation happens frequently in medical imaging, for example, in screening tasks where the disease prevalence is low, so the non-disease class overwhelms others. So in such a task, if a classifier blindly predicts all cases are in the prevalent class, then this will be a useless classifier because it doesn't use any information about the patient or imaging data. It just classifies all cases blindly, but it will have a high overall accuracy because most of the cases will belong to the prevalent class. And one may think that this is a well-known situation in medical imaging, and most investigators will avoid using this metric by itself. But in other types of imaging and in classification problems in other areas, this might still be a problem. So here's a paper from about 2 years ago about classification and Earth resource remote sensing. The title of the paper is Overselling Overall Map Accuracy Misinforms About Research Reliability. So the authors of this paper did a topic research or topic search using the Web of Science core collection and covered the top 10 journal groups in the past 50 years. They looked into what metrics the papers were using to evaluate the performance of the classification algorithms. They found that a large majority of the papers use overall accuracy that I defined in the previous slide as the only metric, which is of course problematic. Less than about a tenth of the papers use what they term producer's accuracy and user's accuracy. And translated to medicine, producer's accuracy means sensitivity and user's accuracy means positive predictive value. So less than 10% of the papers use sensitivity and PPV. And even a smaller minority of the papers use all three types of accuracy to look at performance. So using overall accuracy is a problem that's still ongoing, at least in other fields. Another source of motivation for us is that performance metric reports can be inadequate or inappropriate. The table you see in this slide is taken from an article in an engineering journal with an impact factor of 3.4. So this is a journal with a pretty respectable impact factor. In this article, the authors used a total of 65 cases and looked at the performance of a machine learning algorithm in terms of accuracy, recall, and F1 score. And they reported 4 significant digits here, while they had only 65 cases. So the use of 4 significant digits may imply an exaggerated confidence on the precision of reported metrics. But more importantly, they did not provide confidence intervals, neither in this table nor anywhere else in the article. So we do not know when the same machine learning algorithm is applied to the population that these test cases represent, what is the range where the metrics are likely to lie in. And the last example that I have is from medicine. This is a paper by Deeks and Altman, where they commented on a paper that appeared in the British Medical Journal. It is titled Sensitivity and Specificity and Their Confidence Intervals Cannot Exceed 100%. And Deeks and Altman say that the investigators in a previously published paper reported a sensitivity of 100 with 95% confidence interval 92 to 108%, and a specificity of 89%, with a 95% confidence interval of 74 to 104%. Again, the sensitivity and specificity nor their confidence intervals should not exceed 100%, and such impossible results arise when the standard large sample method for calculating confidence intervals for proportions is used when the proportion is near 0 or 1, or when the sample is small, or both. And this might still be a problem for investigators using MIDRC data. So this brings us to the goals of Technology Development Project 3C. A major goal is to develop information and suggestions on task-specific performance assessment metrics and analytical methods for machine learning algorithms. We identify analysis resources, including research articles, book chapters, software packages. We coordinate with our sister project, TDP 3D, on how to best use sequestered data to provide reference analyses and performance benchmarks. And we coordinate with the collaborative research projects to ensure consistent use of performance assessment approaches and metrics. And I would like to put the work of our project into the wider perspective of MIDRC. We do have a data collection, design, and evaluation ecosystem in MIDRC. We're collecting large representative data sets for well-defined tasks, working to ensure that the data sets have high quality and have high diversity in terms of attributes such as patient age, race, gender, and be transparent about these attributes. We already have a mechanism that we are refining for task-based distribution and sequestration of the data and for promoting independent testing. And the data sets are already available and getting larger in time, available to developers of COVID-19 AI algorithms around the world. So combined with other parts of this ecosystem, the goal of our project is to help with the evaluation, performance reporting, and head-to-head comparison of machine learning algorithms applied to MIDRC data. And the first goal of our project is to develop a decision tree to assist MIDRC users in selecting metrics and reporting performance. We believe that this will help researchers from different fields who employ MIDRC data select task-based performance metrics. For example, it may help investigators who come to MIDRC from a pure computer science background. We believe that this effort will encourage use of consistent metrics for similar tasks and help comparison of results from different studies. And we believe that this will help stakeholders put reports from MIDRC into a proper perspective. In coordination with the rest of MIDRC, including other collaborative research projects and technology development projects, we try to translate algorithm tasks to analytical descriptions. And we do this by asking users a series of questions to guide them through a decision tree for metric selection. The final leaf of the decision tree provides suggestions for metrics and relevant resources. And I will try to explain what I mean by algorithm tasks and analytical descriptions in the next few slides. But first, I want to summarize our coordination with the collaborative research projects, or CRPs, in MIDRC. We have met with about half of the CRPs to discuss their tasks and how we can work together for identifying focus points on metric selection. Besides these meetings with partners from MIDRC and other CRPs, we have also invited a number of other experts to our group meetings to get their advice, including Drs. Brandon Gallus and Jean Pinello from FDA DITSER for discussions. Now, moving on to algorithm tasks and analytical descriptions. A developer or a researcher may want to design and then evaluate a machine learning algorithm using MIDRC data, or they may already have designed an algorithm and they may only want to evaluate it on MIDRC data. In either case, there is an algorithm task that they should have defined involving several components, such as the specific purpose of the algorithm, the patient population, the input data, the reference standard for evaluating the algorithm output type, and other components. I just want to give you an example to make this more concrete. And we will follow this example through the rest of the presentation. So this is the example task for the presentation. The specific purpose of the machine learning algorithm in our example is to classify chest X-ray images known to include pneumonia as COVID-19 pneumonia versus other types of pneumonia. One may discuss whether this is a clinically useful task or not, but I'm basing this on a paper that was published in Radiology earlier this year, and I've seen multiple other papers that design machine learning algorithms for this purpose. So researchers will investigate this type of tasks. Next, the patient population. In this example, COVID-19 negative patients were patients who underwent frontal view chest radiography, were diagnosed with pneumonia, and underwent imaging between October 1st and December 31st, 2019. Since the data is from the US and this period predates the pandemic in the US, one can presume that all these patients are COVID-19 negative. Patients younger than 18 were excluded from the COVID-19 negative data set. COVID-19 positive patients were patients who underwent frontal chest view radiography and received a diagnosis of pneumonia and who had a positive reverse transcription PCR. Patients were excluded if chest radiography was performed more than 5 days before or 14 days after PCR confirmation. As we can see, this is a case control study, and this has some implications for the metric selection, as I will come back to in the demo. The input data was frontal chest X-ray performed using systems from 4 different vendors, and I already mentioned the reference standard. Now, the algorithm had 2 types of outputs. One is a continuous score for COVID-19 positivity, and the other is a binary output, which is obtained by thresholding its continuous output at a pre-selected threshold. The analytical description of these 2 outputs are as follows. For the first type of output, where the output is a score, is a binary classification task with negligible variability or uncertainty in the reference standard, and non-binary machine learning output. For the second type of output, where the machine learning output is thresholded, is a binary classification task with negligible variability or uncertainty in the reference standard, and a binary machine learning output. As you can imagine, there may be many different, there may be many algorithms with different purposes, patient populations, reference standard determination, etc., compared to the previous slide that end up with the same analytical description. Conversely, if some of the components in the previous slide were changed, one might end up with a different analytical description that may require different metrics for performance evaluation. So how do we go from the algorithm task to an analytical description? We do it by asking the user a number of questions and guiding the user through a decision tree. Now I'm going to show you some screenshots and live demo from using the interactive decision tree that's under preparation to try to explain better. The first screen that you will see is this welcome page, where we currently have defined 5 major analytical tasks: classification, detection and localization, segmentation, time to event analysis, also known as survival analysis, and estimation. We have what we call hover text over each task to help the user make a choice, as shown here. If you hover over classification, you will see the task. Classification aims to distinguish between different categories in medical tasks, such as disease, diagnosis, or prognosis. So this description, as well as descriptions of the other tasks, are aimed at helping the user make a choice at this level of the tree. If the user feels that they made a wrong choice as they go along the tree, they always have the option to move back and change their choice. Now, I'm going to switch to the web browser to show you the live demo. Just give me 1 second. Okay, so when the user clicks on the classification task button, we arrive at this window where we ask the user if there are 2 classes or more than 2 classes in the classification task. Again, that's because there are different and specialized metrics for these 2 choices. If you hover over the options, let's see. I don't see the hover text now. Oh. Give me 1 more second. Okay, sorry. Yep, this is the right window. So we see the how many classes, categories does your classification task involve, and 2 classes and more than 2 classes. And when you hover over these texts, you see again these hover text to help the user. So let's say that the user selects 2 classes, which is the case for the example we are following in this presentation, where we're trying to distinguish between COVID-19 positive and COVID-19 negative pneumonia. When we click that button, we come to a window where the user is asked about the reference standard or existence of a ground truth. Is there negligible variability? And I should add, is there negligible possible error in the reference standard or not? Because if this is not negligible, then one may use metrics that are based on agreement, which is a different type of metric than those that may be used when a gold standard exists. In our example, based on the fact that all COVID-19 pneumonia cases were recorded in the US before the beginning of the pandemic, and the assumption that the false positives and false negatives with the PCR test are negligible, let's say the user selects negligible variability. The next question in the next window is about the machine learning output. Is it binary or is it a non-binary score? We will visit both of these because the example we are following had both types of output. When we click on the binary output for the machine learning algorithm, we see a page for suggestions for performance evaluation of a two-class classification based on reference standard with negligible variability and binary machine learning output. Here we have a 2x2 table that summarizes what the machine learning output is with respect to the reference standard, and then 4 metric pairs that we have considered so far: sensitivity specificity pair, precision recall, positive predictive value, negative predictive value, and positive likelihood ratio, negative likelihood ratio pairs, and other metrics that combine elements of these pairs into a single metric. For example, the F1 score is the geometric mean of precision and recall. So let's click on one of these, sensitivity specificity pair, and we see again some basic definitions and then some resources. The first resource shown here is a reference to a book for approaches to find point estimates and confidence intervals. So that reference is also here. So when I click on that, it will take me to a page for a book. Some basic information about the book, how to get online access. And by the way, many institution libraries may have online access to this and other information. So I go back to the previous page and look at more resources. There's a reference to an R language package that to calculate these metrics using various methods to find the confidence intervals. And these different methods may be important to prevent mistakes, such as the one I mentioned at the beginning of the presentation about the upper limit of sensitivity confidence interval exceeding 1.0. When we click on the related link, it will take us to the related R programming package right here, including information about how to install and run it. Now, go back again, and the third paragraph here is a note about clustered data. Most methods are designed with independent data in mind. And if you have clustered data, you need to be careful not to underestimate the width of the confidence interval. What do I mean by clustered data? In our example, there are multiple chest x-rays per patient, which form a cluster for that patient. And the results from these multiple x-ray examinations are expected to be correlated. So if you use the results from each chest x-ray directly for confidence bar estimation, you will likely have an underestimation for the width of the confidence bars. Okay, so let's go back and look at the second pair, precision and recall. Again, we have some basic definitions here, and then some resources, reference to a book, and R package right here. And another note about prevalence. As we know, precision, or the positive predictive value, depends on the prevalence of the positive class within a data set, unlike sensitivity and specificity. So this note is about that, about not using the simple formula above, shown here for precision, about not using that simple formula if prevalence in the test data set is different from that in the intended population. And for the case control study in our example, it's likely true that the prevalence of the data set does not reflect the true prevalence. When this happens, but when one knows what the true prevalence is, then one can use a method explained in this book and the paper. You can still calculate the PPV, but in our case, the prevalence may keep changing in time as the pandemic is evolving. So it's probably better not to use precision recall as a metric. And after reading these notes, The user who may have such a data set where the prevalence is not representative and the true prevalence is unknown could refrain from doing precision recall analysis. Okay, now I go back again. I will not click through the other pairs, but still move further back and look at the non-binary score for the machine learning output. Here we arrive at a suggestion page that includes 3 choices: receiver operating characteristic analysis, precision recall analysis, and predictive receiver operating characteristic curve analysis, which is based on PPV and MPV. So let's click on the ROC analysis, and we have some basic information, 3 basic reference papers shown here, and then 3 options as metrics: the area under the ROC curve, the partial area under the ROC curve, and selection of a single operating point. Clicking on the ROC curve, again, we find some basic information about what the area under the ROC curve means, and then resources and nodes. The first resource is an R package that provides tools to visualize the ROC curve and find the area under the curve and confidence intervals. The second resource points to the IMRMC software developed by Brandon Gallis from the FDA, which handles the figure of merit, the area under the ROC curve in our example, but also more complicated analyses such as multi-reader, multi-case ROC analysis. The third resource is MET software that provides a platform-independent software package for ROC analysis that includes many alternative ROC analysis approaches, and so on for the fourth resource. Again, clicking on one of these, for example, clicking on the IMRMC button, takes us to the a page for about how to install and run the IRMC package. So that was an example of some branches from the classification tree. And let me go back to my presentation. Needless to say, this is work in progress, and we're still refining the language and references. And you may have already noticed some items that we need to polish in the few examples that I showed you. So moving on to the next slide. That being said, the classification branch of the decision tree will be made public soon on midrc.org. And we hope to improve this branch as well as the other main branches listed here with feedback from the community. Now, zooming out from the details of the decision tree to a wider perspective again, combined with other parts of MIDRC ecosystem, our project is expected to help with the evaluation, performance reporting, and head-to-head comparison of machine learning algorithms applied to MIDRC data. In summary, Technology Development Project 3C is working on a decision tree tool for metric selection and reporting for machine learning algorithms applied to MIDRC data. And the first main branch on classification is to be released soon on midrc.org. And I could not help not make at least one tree pun. Please help our tree grow with your feedback. And I would like to acknowledge and thank all the members of TDP3C listed here: Natalie Bowen, Karen Drucker, Mary Ellen Geiger, Mike McNitt-Gray, Ting Ting Hu, Grace Hyun Kim, Kyle Myers, Emily Townley, and Heather Whitney. And finally, I would like to briefly mention additional resources from the 3 MIDRC partners that include metric selection, evaluation, and reporting in AI. The first and the second editorial papers by RSNA and AAPM are on guidelines for AI publications. And the third website by ACR is on independent evaluation of AI algorithms. And a lot of investigators are publishing with data related to MIDRC So I'm not going to try to give you a full listing of that, but I just wanted to mention two recent overview type papers from MIDRC about, again, guides on using MIDRC as a resource. Thank you again. This concludes my presentation.
Thank you, Berkman. That was very informative, and I invite the audience to put any questions they have in the chat. And I'm sure many of you out there are thinking about your prior papers, saying, did I do the right one? Was it unbalanced data? This is really going to help. And I'm really looking forward to this tree becoming fully done and fully used by not just MIDRC folks, but everyone across. The example you gave was on COVID, but this can be used on many. And I like how you used an example because it always helps me to understand when there's an example given. So I don't see any questions in the chat. So I have a few, I think. You showed that there were parts of the tree that talked about ROC analysis and precision recall. And that's something that confuses a lot of people out there. When do we use one, and when do we use the other, and when do we use both?
Great question. So I think, there is, I think, a general maybe confusion in the entire community. And when we think about ROC analysis, it uses both the true positives and false positives to plot the curve. So it uses, in the 4x4 table that I showed, it actually uses the entire table. Whereas precision recall analysis, it doesn't use the true negatives. So the sensitivity is defined, again, as I showed, the true positives versus all positives. And then the PPV is true positives over all cases that were called positive by the device. So the true negatives never enter the equation for precision recall. And the importance is that, this started earlier in the literature about retrieval algorithms or algorithms for search. And the idea is that, again, if you're searching and if you search the entire web versus if you search a portion of the web that's maybe gonna include, where the false positive or the true positives are different, then you might get different results if you use sensitivity and specificity. So the idea was that, in problems such as that, the precision recall is useful. And likewise, in imaging, I think a situation where this might be very useful is in location-specific analysis. Because again, when we're trying to find where, define a true positive as a correct localization of something that you want to localize, that's great. But then how do we define a true negative? In an image, if I don't put a circle or a box in a normal corner, it's a true negative. I move that box a little bit further, that's also a true negative. I move it more, it's also a true negative. So a true negative in a detection task is very hard to define. And by avoiding the true negatives in its definition, I think precision recall could be a good metric. And people have also suggested that precision recall is also a good metric when there is a high imbalance between classes in a classification problem. And I think it is sort of maybe, if you use ROC analysis versus precision recall for those imbalanced situations, I think you may end up with similar power when you're trying to find a difference, for example, between two techniques. But you have to be careful to interpret your data correctly. In other words, if it's a very unbalanced problem, let's say it's a cancer detection task where you only have five actual positives over 1,000 cases in screening. So you can have a very high specificity, but still the total number of false positives that you get can be high. So you might be misled by thinking that, oh, I have this very high specificity, it's a great algorithm, but you have to take a few more steps to interpret it correctly. So precision recall might be helpful in those kinds of problems as well.
Thank you. That's a very clear explanation. So with this precision tree, it's really growing, and it's going to include so many different tasks. And with examples, I think as more and more folks come into the AI field, they're going to find it very useful. It makes the evaluation and what statistics to use, what metrics to use for evaluation. It's very user-friendly. I think also it will, I'm looking forward to hearing as people use it and maybe post on some chat box or something. What did they end up using? And like you said, help us grow the tree. So I think that will be an ongoing discussion, and that will be very useful. I also want to invite anyone else on TDP 3C if they have questions or want to enhance any part of this. I think will be very useful. It's good that we do have a question here. It's good that you're checking with the various other groups in MIDRC, because it's the CRPs that are developing AI, but they will be relying on the decision tree to come up with the appropriate metrics to evaluate theirs. Now, there is a question here. Thank you for the fantastic talk and appreciate the set of tools being developed. I'm wondering if this would also be extended to account for joint detection estimation task.
Yeah, I think that's a great question, and I think we should. And I didn't go into the details of the different parts of the tree where we look at detection and estimation and how the two are related. And I think joint detection and estimation is a good example where we have an overlap of these tasks, and we definitely will look into it.
Yes, thank you, and I look forward to that.
Task and another metric from the detection task, or there might be joint detection and estimation, but that's definitely something that we will be looking into. Thanks for the question.
Yes, and sorry about that. You froze, and I think it was my internet at my end. So I had, so for me, you stopped talking. You were still talking. Yeah, thank you. And if there's no other questions, we can close. I want to thank Berkman for making such a complex, complicated topic very simple to understand, and also to all of TDP 3C for making it, bringing it to us as in a user forum to really make it so that we can evaluate our systems in an appropriate way. Any closing remarks? And I think I might be frozen again.
I can hear you.
Oh,
fine.
Okay. So we can close this session, and we have this monthly seminar monthly. So we welcome you back next month in December. We do have a December one, right? Yes.
We'll be back in January.
We'll be back in
January. Yes, we're skipping December. We'll be back in January. Thank you all. Thank you, Berkman, very much.
Thank you.
Thank you all for joining.